and so forth. And so today we're going to start a little bit with multivariate normals, but this is really the pivot toward multivariate analyses. And so I like to do matrix algebra first because matrix algebra is kind of the language that a lot of people write in for matrices and so forth. And your homework this week is based on that. Boy, that's fuzzy. But then after that, after matrix algebra, we get into doing things with models, because ultimately it's not the algebra we really care about. It's the results, it's the data, it's that p-value so you can graduate, right? Is that how it works? Please.
Go back.
There we go. Yeah, I'm tired of the little flicker, but I hope you're not epileptic. So we're going to start with models today. And we're going to talk about multivariate linear models. We're going to start them with my favorite models, which are the empty models, which I understand not everybody calls empty models, but I like them empty. Because this will time the multivariate normal distribution back to data, right? So if you remember the very beginning of the class, the first linear model we put up had one outcome, said y was equal to just an intercept plus error. Remember that? What was the intercept in that case? What was it equal to? The mean of the data. And the residual variance happened to be the error, the variance of the data itself. So similar to that, a multivariate outcome, a multivariate model where you have more than one dependent variable, an empty model for it will give you the multivariate analog to it, particularly in multivariate normal. So instead of just one mean, you'll get a mean vector, right? Or a series of means, one for each variable. And instead of just one variance, you'll get a covariance matrix, where the diagonal of that will have each variable's variance, and the off diagonal of it will have the covariance between any pair of variables. So that is tying the matrices to the models and so forth. But then we're going to jump into maximum likelihood estimation for it. And we're going to dive in through path analysis. So I'm going to start off with an introduction as we go along. Before we start, any questions? Everybody's looking happy. For those of you who came in a little bit later, no quiz today. So consider yourself lucky. No, I don't know if that was it. People were coming in here with a very negative attitude. They were going to fail this quiz and everything else, and you just absolutely passed. All of you got 100%. All of you also got 0%. Okay. So, next 4 weeks of lecture are provided to give an overview of multivariate linear models. So these are models for more than one outcome or dependent variable. This is what happens, but this is what multivariate statistics is supposed to be for. Our focus will be on models where the dependent variable is plausibly continuous. We say that because we will use a multivariate normal distribution for the error. So the variable itself has to be somewhat continuous because multivariate normals are continuous distributions. Plausibly means how many times have you taken a Likert scale and done like a factor analysis with it? Anybody? I've seen smiles. Vane has. Anyone else been like Devane? Walter? No, just kidding. No, it happens sometimes, but generally speaking, we want to look for continuous data for this. There are other multivariate models. So this is generalized models, is what they're called, with outcomes that are not quite continuous. Or you could have mix and match. Maybe one outcome is continuous, maybe one is not. But we are not going to cover those in this class as much. That's a different class. Moving forward. So I'd like to talk about the classics a little bit. That was not my favorite subject, like reading and old books and stuff. I don't read. I don't like books. I'm hating on everything. I hate science fiction. I hate books. What do you like?
And now you're writing them.
Maximum likelihood. I hate my book. Yeah, I have the wonderful pleasure of having co-written a book that is now outdated, essentially. So there you have it. Yeah, terrible, isn't it? Yeah, I'm just a critic, a really good critic. Anyway, our classical approaches. If you look at the classical textbooks, classical in quotes, so things that you probably will see in other places on campus, it might even be in the multivariate class being co-taught in psych these days. you'll see multivariate linear models, and they'll be under the heading of multivariate ANOVA or MANOVA, or multivariate regression. And typically, depending on the book that you read, it goes something like this. Multiple variables, ANOVA. Matrix, 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 results, go back to univariate. Right? So the whole question and answer part of it is sort of a weird thing, and I have seen this approach to be limited in its ability to scale forward, and this is part of the issue with it. We're still going to do multivariate ANOVA, we're still going to do multivariate regression, but the way that we're going to do it is with modern approaches. So you can go back if you ever are needed to go back in time to give a multivariate result. We can go back and do that, but ultimately I don't think you will. So to tie the two together will be there. Generally speaking, the multivariate ANOVA approach and multivariate regression approach use least squares estimation, which for univariate models is equal to maximum likelihood, but in multivariate models it has a lot of problems. First of which is if you have any outcomes which are missing, you've got to throw away the entire case. So that is to believe the results from that analysis, where you throw away what we call case-wise deletion, you have to have some really, really, really hopeful beliefs about how data are missing. We'll talk about that in a few weeks. These methods offer very limited methods for setting up covariance matrix structures. Now, whoa, hold on a second. Last week we talked about covariance matrices. The thing about multivariate models, and we're going to see this in just a little bit, part of the issue when you do things with multivariate normal is that darn covariance matrix. And I say that, darn, I feel like, shucks, that covariance matrix just gets in the way. I should just feel more free to cuss in class, but that damn thing that ruins everything. Can I say that? Just that damn covariance matrix. That's the problem with multivariate. The thing is, every time you add an outcome, because you think it would be a great part of the study, and it probably would, that thing grows, right? But it doesn't just grow by one thing, it grows by all the covariances as well, right? It's not just the variance you add, but also the covariances. So you quickly see that in statistics, we oftentimes talk about power and sample size and so forth, but power is related to the number of parameters you can estimate, right? So every time you add a covariance, you're adding a parameter. So the bigger your covariance matrix of this multivariate outcomes gets, the less power you'll have for the same sample size. Because every parameter you add essentially costs you power to go and estimate it. So in the classical approach, there were two structures available. One that came about through repeated measures ANOVA, which was something called sphericity, which led to compound symmetry. These are words we'll see in a few weeks. And one that came about with MANOVA or multivariate regression, which said, screw it, I'm just going to estimate everything, power be damned. That was it. Somewhere in between lie most data. So if you're in least squares estimation land, it's hard to tell which method you should use, and it's also hard to tell which one would fit best. So one of the other reasons why I like to switch away from these two methods is that we have much more options as to how many covariances you want or you need in the analysis itself to really dictate a good fit to the data. Furthermore, these methods also didn't allow or don't allow for different sets of predictor variables predicting each outcome. If you have a repeated measures design, all right, and you're giving someone, let's imagine, the same test, or better yet, I know some of you are in HSES, right? So you do fitness type things or whatever. Fitness things, and clearly I'm not part of that, but that fitness stuff. I don't hate it, though, that's the thing. But if you're taking some physiological measurement repeatedly, right, be it blood pressure, be it force plate something or other, I'm getting some of your advice. Am I speaking right? This likely is fine, but if your design, maybe you want to predict that with the same predictors over time, that may be fine. But if you're in a different setup where you've got, maybe you're not in HSES, or maybe you are, maybe you have all those repeated measurements, but then you also collect some type of personal variable, some type of psychometric variable, like an inventory, a scale, a motivation scale, or whatever it is with it. To do the analysis all together, you may have different predictors for different parts of the variables. In the old way of doing things, you couldn't do that. You have a predictor, it predicts everything. Doesn't matter whether you need it to or not, it just does. And it's sort of how the software kind of set it up to make it work. These methods also didn't give good information about model fit. So when I was telling you they sort of had limited approaches to covariant structures, which we'll see in a little bit, a couple of weeks, you couldn't tell which one fit best, right? You sort of had to go with the super limited version and sort of adjust and hope that worked, or the super powerful version, the full-blown version, and hope you had enough power for all your effects. But you couldn't tell whether or not one actually fit better than the others. And the methods that we're going to talk about now will be able to give you that information. And finally, so that's model fit, that's model comparison. Model fit's also there too. If you fit the limited information or the kind of restricted model, the compound symmetric model, the repeated measures ANOVA version of it, you couldn't tell how far off you were from the best fitting model itself. So, I don't teach these because I think they're relics of the past. They came along before we had computers, and we've gotten much better at statistics. The other reason I don't is because all of the things you're going to learn here are these, should you meet all the assumptions. Right? Should you have complete data, should you pick the specific covariant structures I'm talking about, you'll get the results that you would get back in multivariate ANOVA, multivariate regression. So what I'm going to teach you goes beyond all of that, and it's a little bit more flexible for you. So I say that because the word subsumed shows up, right? These methods have been subsumed into bigger things. And I think that concept is hard for your advisors to understand. I said it. Not all of your advisors. But the advisors I've worked with before were, can't we just do a repeated measures ANOVA? We are, but we're doing it better. Right? That's what we want to be able to say. So what we'll do are talk about two large classes of these models. First being path analysis, path analytic models. And we typically see those in structural equation modeling software packages. So we're going to start there with Lavaan in R. The second part is linear mixed models, and they're typically through mixed model software. We'll go into the NLME package or LME4 in R. So the interesting thing about this is sort of where we're at our upper limit in statistics for packages. Right? If you go in either of these directions, you're going to be doing essentially the same model. The nuances will change. And not all packages give you all the benefits. So the differences that you see here comes from software. The theory that underlies each is identical. Right? It's the software that implements the different parts of that theory for different groups that show up. So we're starting with path analysis mainly because I think it's a lot more of a direct modeling approach for each of your outcomes. Right? So we're going to be able to put each outcome in a model and then predict it with a series of regression or predictor variables, just like we would with a univariate model, but each one can have a different set. We'll switch over into the mixed model packages for other reasons as we come up. And ultimately, going with all of this is, we're going to see a scorecard in just a bit, but really what we're after here, when we have multivariate normal data, we actually have what we call a quadratically increasing number of parameters. So first of all, parameter, right? It's a model term, something that the package has to estimate. And in the likelihood version of it, it's some dimension that you have to go and find the peak of for what you do. So every time you add an outcome, in a multivariate normal sense, you get a quadratically increasing number of parameters with that outcome. So having lots of parameters creates a ton of problems. Right? If you have small sample sizes, good luck estimating them. Right? The maximum likelihood package will break. It'll tell you it did not converge or some other stuff. You'll have difficulty with power. Let me just mention that. And the more outcomes you have, the harder it will be to get really restricted models to fit. By restricted, I mean direct analog to something like repeated measures ANOVA. So common solutions to this curse of dimensionality, and it's really written like that. It's called the curse of dimensionality. The common solution are to put very specific structures onto this covariant matrix. So rather than allow all variables to have a different variance, one easy way to restrict it is to say everybody has a common variance. That's one easy way of this. That's a type of structure itself. Other types of structures exist. In fact, there's tons and tons and tons of them. In path analysis software, we're not going to see those as much, but they show up a lot in mixed model software. Depends on the field that you're in, mainly. So, but the key in multivariate analyses is you have to find a structure that fits your data approximately well, as good as what you would have if you had all the terms in it. If you don't have that model fit, you can't go forward. You can't report the results. In fact, depending on the type of model you're using, like a confirmatory factor model or structural equation model, there are some very strict standards for what model fit happens to be. And you may look at your model parameters, your regression weights, and everything else and think, oh, these are amazing, but they're not valid unless the model fits. Right? So we get this new complication that comes up that we didn't have in univariate models, in that we have to find a covariant structure that fits as well as estimating everything. So that's what shows up. So this is the biggest difference in multivariate versus univariate models. Remember the model for the variance? Right? It was something to do with E. Right? I put that up on the board. There was E on the end. That's the error. It said error was normally distributed. It had a zero mean and it had some type of estimated error variance. That, with one variable, there's only one way that you can do that, which is an estimated variance. Right? It's called saturated. It fit perfectly every time. So model fit wasn't an issue in univariate statistics because every time that you fit an analysis, you had perfect model fit. Did you know that? You've all been doing perfect model fit ever since you started statistics. How do you feel about that? Not you, Megan, but the rest. I say that because Megan's been doing multivariate. I'm trying to pick on this row. I'm going to make my way back. Jake, you're next. Model fit's an issue particularly because we have to have all these variances and covariances. The damn covariance matrix gets in the way. So we have to find a good structure that balances number of parameters with the fit of the data. And any non-saturated model, any model where we don't estimate all the parameters. By the way, the word saturated means estimate everything. Everything that's possible. So if we have two variables, there's two variances in the covariance. That's a saturated model. We have to show that our model fits just as well as the saturated model itself, and that double star there means the fit. What model fit means varies widely depending on which field you're in, which field publishes paper. So this is a scorecard I tried to come up with, checklist, if you will, about the differences in the two approaches. And I've thought a long time about how to teach these two approaches because I want you to learn both. I really wish I had a program that would do both and I didn't have to switch between the two because it's a pain in the butt. But here's why I have to switch between the two. So, here we go. Actually, I have three here. These three columns tell you the features that show up, right? You've got your classics, multiple MANOVA, M regression. We put repeated measures ANOVA into this group too. That's right in this column. Path analysis, that's what we're going to learn today. And next week. And then mixed models, which shows up after spring. So the first feature, dependent variables, your outcomes. Can they predict other dependent variables? It's a necessary thing to do. Have you heard of mediation models before? A mediation model is one where you have a variable x, a variable y. If I were to draw an arrow to it, x predicts y. This is like saying y equals beta 0 plus beta 1x. But perhaps there's some crazy other variable here that mediates the relationship. M is predicted by x directly, and if you think about this pathway from x to y through m, x now has an indirect effect on y potentially as well. Right? So what this is a multivariate model. This is an outcome. This is an outcome. Both of those outcomes are dependent variables. But the key in all of this is that one dependent variable, the mediator, is actually a predictor of a different dependent variable. So dependent variables can predict other dependent variables simultaneously is sort of a definition of path analysis. Sometimes in econometrics it's called simultaneous equations, panel models, there's all sorts of names that show up in different parts of fields. Your classical approach to doing this absolutely won't do this. Your path analysis approach absolutely will, because that's where it started. Your mixed model approach doesn't do this either. And that is a key difference. This little yes, no right here makes me mad. Mixed models can do it, but not the way that software is built. So, next feature. Do we have variable-specific modeling options, right? So can we take, if m and y are our two variables, can we predict m with x, z, and w? We'll predict y with a, b, and c. Right? That's what I'm talking about with variable-specific. It helps us develop models precisely. Right? Some things may mediate, some things may not. Some things may not be significant. We can drop them from the analysis if they don't have an impact and save some power. Classical approaches, no way of doing that. Good luck. I'm railing against classical. Heat. In path analysis, yes, you can, and we can do it directly, which is what we've known all along, by the way. In mixed models, we can, but the way we've set it up is with a series of dummy codes and interactions. So that becomes a little bit harder. Next feature, robust maximum likelihood estimation. We mentioned maximum likelihood last week. There are variants of maximum likelihood that show up in these models. The first being something called robust, and this provides protection if your data aren't quite as peaked as the normal distribution says, or maybe they're overly peaked, lepto or platykurtic. Yet another wonderful stat term. We want to tweet that. That's a great kid name. Platykurtic? No, maybe not. Kurt, that would be good. That's good. That's good. Those of you who are thinking. Some of you are thinking that's not even a good name for some inanimate object, like the heater or like the countertop, or that's platykurtic, the knife. No. Anyway, lepto and platykurtic, if your data aren't quite normal, that's what it's saying. They're too peaked or too flat. You don't get any help in the classical approaches. You do actually get it in both path analysis and mixed models, although the mixed model software doesn't go as far as a lot of the path model software does for it. So this is a nice advance of it. It's maximum likelihood when the distribution assumption isn't quite right. So that's one version of ML, when the distributions aren't quite right. The other is something called residual maximum likelihood, or REML. And this is a big thing for me because in ML, as you know from this week's homework, you have to divide by n for the covariance matrix, meaning all your variances are divided by n. And then in basic stats, you learn that it should be n minus 1 to make unbiased effects. Well, guess what? In path analysis, which gets run without residual maximum likelihood, you will get biased estimates of your covariance matrices, because essentially it's divided by n. So for smaller sample sizes, it makes a big difference. So this is a problem. Believe it or not, the one thing that the classical approaches took care of was that. They knew about the bias. They could correct it using the trick of essentially the analog to n minus 1. Path analysis doesn't have a fix for it, but residual maximum likelihood is a method that does give you unbiased estimates, and mixed models give that to you. So another reason why I'm teaching you these two methods are right here. In some respects, mixed models are unbiased. They give you great estimates, help you with the type 1 error rate issues, and so forth. But they can't let dependent variables predict other dependent variables, so they're limited in a lot of respects. They don't have to be, but it's just where software is right now. Okay, how we doing? My motivational slides are not really motivating me. This hopefully sucks less than matrix, blah, or blah, 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 transpose, blah, 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 product. Does that kind of summarize last week? Does that go pretty well? All right. The next thing that's interesting is can we incorporate random effects? Now, what are random effects? These are terms that are the technical definition. You put a distribution on them, but where they're useful is if you have additional dependencies in your data. So, for instance, if you have clustered data, right? Children within classrooms, within schools, and so forth. Or maybe you have longitudinal data. observations across time within a person. These are, the dependency in those are modeled using random effects. Classical approaches have no ability to deal with those. Both path analysis and mixed models do. In fact, that's the definition of why they're called mixed models. There's fixed effects, which are the betas that we know, and then the random effects as well. The path analysis versions of them are pretty limited, though. You can get two-level nested data. If you have cross data, if you have more than two levels, if you have all sorts of stuff, mixed models are where you go. M+ does a few more of these than just what we see in Lavaan. Can you get multiple covariance? So the next issue is multiple covariance structures. Why we want that is because of the curse of dimensionality. No is the answer to classical. Some in path analysis and lots in mixed models. Again, we have approximate model fit indices. We talk about when you do fit a limited covariance structure, how bad it is, how far away from perfect it should be. No for classics, yes for path analysis. In fact, it's a whole cottage industry of fit in path analysis. And then no for mixed models, believe it or not. And finally, can we get different denominator degrees of freedom methods? Denominator DF, what the hell is that? Talk about that in mixed models because it does show up there. But if you have smaller sample sizes and you have multivariate data, your degrees of freedom, remember the F table? That, by the way, is actually going away. The F test had a denominator that had degrees of freedom in it. It was essentially like the number of people in your sample. Well, if you have data that's multivariate and there's a covariance between those observations, your sample size isn't exactly the number of observations, it's something smaller than that. So how do you adjust the degrees of freedom down from 1 degree of freedom per observation per person to something that's smaller? That's what these methods do. There. So, how are we doing? All that sums up to tell you I need to teach you both. All right? Both methods are what we're going to learn. My plan for this is we'll spend 2 weeks on the path analysis sort of side of things, and then we'll spend 2 weeks on the mixed model side of things. It may take an additional week or two after that. We'll see. In terms of homework, the next homework, homework 3, which is not up yet, not even available yet, and homework 4 will be the same assignment. I kid you not. I'm going to give you the same assignment, but I'm going to ask you to do it with path analysis one way and with the mixed model the other way. Because the mixed model side of things really starts to confuse how to get the effects out. But it fits very well with what we did in homework 1 with interactions and the GLHT function. And path analysis is a little bit more direct. You might actually like it better, but it suffers from the issues of Raimola and all the other things to deal with. So I want to learn you both of those. Is that a good way of putting it? It'll make the grammarians in the class frown. No, looking at some of them myself. Does anyone bother you? Is grammar important to you? I look at the back of that door with apostrophe pros and cons. And that's sitting there mocking me because I remember the first week's slides I had one of those in it. Oh my God, no. It bothers me. Anyway, so I want to teach you both methods. In the future, I fully expect to not have to do this because if I could have my way, path analysis would do all the things that mixed models do, and we'd have software that has it all built in, and we wouldn't have to worry about that. But right now, we're not at that point. So I'm sort of teaching you, trying to show that I'm teaching you things that are sort of the state of the art. So that means when you get out, you'll be able to move forward with it, hopefully, as well. Get out. Break out of this place from the PhD. So here's some simulated data for an example today. This example will show up again next week. There's a paper I found online by Pajares and Miller, The Role of Self-Efficacy and Self-Concept Beliefs in Mathematical Problem Solving, a Path Analysis. All right? So, do you believe you can do it? All right. Self-concept, I don't know about that. Whatever that is. Basically, do you believe you can do math? If so, do math, right? How does that work? So we'll have simulated data. I generated this based on the results in this paper. We had 350 undergrads carry through with this. These are all the variables, but we're only going to focus on a couple of these today. This is the big path analysis where we're headed. That thing is, well, this the schematic diagram itself of a model. Now, by the way, I wrote this. It says path model on the top. This is not a model. This is a representation. It's a schematic representation. Remember that. There are some of us in the quant world, myself, my colleague Billy, we look at this and we go, oh, I'll see this, right? Because to us, a model would be something like y equals beta 0 plus beta 1x plus e. And if this is what you're calling a model, I will ask you, where's beta 0? Right? Because each of these lines is supposed to represent a slope. But the key in all of it is why it's not a mathematical model, or why it's not what we would say is isomorphic. It's not, all the parameters of the model don't show up on this picture. There are ways of making pictures that have all the parameters, but this isn't one of them. But this is what people frequently use. They call the path diagram or something along those lines. But this is what we're trying to do. We're basically saying we want to predict, we think, here's the key, mathematics performance, so how people do on a math test, and the perceived usefulness of math, like high school students, undergraduate students. These are the two ultimate outcomes. And we think all these other variables relate to them in very intricate ways. So for instance, gender might predict high school math experience. We'll see that that's really not the case because curriculum dictates that. May also predict math self-efficacy, how well you think you can do math. But that gender effect is essentially there's no direct effect of it on performance or usefulness. It's mediated by all these other variables. Is what we're saying. Well, we're going to get to that next week because I like procrastinating. Why do something today that you can put off? What is it? Why do today what you can put off till tomorrow? You know what I'm talking about, right? Okay, questions. Looks pretty impressive, right? That's a path model, path diagram. Not really a model, path diagram. You should watch my image. Dark side has donuts. Wow. Yes, correct.
What's the difference between the path model and the EPSY?
Path model and SEM. So in structural equation modeling, it is also a path model usually. The difference is that some of these variables may not be observed. Right? So for instance, performance is really a psychometric variable. It should be a latent variable. And actually, like all these right here, these are surveys. So in a structural equation model, we're going to put a factor analysis in place of the observed variable. Rather than taking a sum score, we're going to allow that to be a latent variable and have what we call a measurement model in place of it. And then we do the path analysis on the latent variable altogether. And the reason we do that in structural equation modeling is because when we put a sum score in the place of something that should be latent, we have if this thing has very bad reliability or even marginal reliability, then all of our regression coefficients will be biased. So to remove the bias from it, we create something called structural equation. Good question. Other questions? Bias is bad. That's what I feel like I'm saying. Bias is bad. It's like caveman teaching statistics. Okay. So, maximum likelihood by multivariate normal. We're going to use Lavaan, a package called Lavaan for estimation of path analysis. So in R, remember R works with packages, and you saw this in the first homework. You had the multcomp package you had to load before you did anything. Multcomp. Yeah, then this homework 2, you've got another package, MVT norm or something like that. The Lavaan package has a great story. So, any of you have any of you used the M+ computer program before? Nodding, yeah. M+ is very expensive though. For a student license, it's like $350 for the cheap one, and then you got to pay them $175 a year to get updates and support and stuff. And if you're a faculty member, it's like $1,000 to buy it, right? And normally I'm not that cheap, but come on, right? M+ has a lot of drawbacks to it. So a group of people created the Lavaan package, and it essentially mimics M+, but does so for free. And as you imagine, the M+ group, of course, M+ is really one professor and his wife, and then people they've hired, like 2 other people. One of his daughter, stepdaughter, and then some programming persons with a 4-person company. Like, I've heard that the person who created Lavaan, or was the lead on Lavaan, was invited to speak at a conference where Bank Mutane, the guy who did M+, was, and Mutane insisted that the other guy get disinvited before he showed up. In fact, he wasn't even allowed at the conference before he showed up. That's how angry he was about it. Right, and so the guy from Lavaan, I think he said he wore a mustache or something really obviously fake around the conference just to kind of... Anyway, so M+ does a lot of what we need it to do. It costs a lot, and then it breaks a lot also. It's very unstable. Lavaan does not nearly as much stuff as M+ does, but for our class it works pretty well, and it's free, and it breaks just as much as M+. So in some respects you get what you pay for, but not with M+. So Lavaan actually stands for Latent Variable Analysis, L-A-V-A-A-N. I don't know, it sounds fun, right? And the default to using Lavaan is a linear mixed model that uses the maximum likelihood with a multivariate normal distribution. So that's what we've been talking about. We talked about multivariate normal a little bit last night. We can use Lavaan to do analyses for all sorts of things, though, right? We could do MANOVA, repeated measures ANOVA, factor analysis, structural equation modeling, and more. So it does pretty good, has a pretty good set of things it does already, and it's not even its full release yet. So let's start with the univariate regression to get used to Lavaan. We're going to take the mathematics performance variable. This is kind of the score on a math test. The way it was computed was there was a 20-item test. It was the number right at 20, which is not a great way of doing it, by the way. Take IRT, take SEM. That's a better way to do this, but for now we're just going to do that. That's our performance. We're going to do an empty model where we predict performance with an intercept and error. And you'll note here my intercept now has a superscript. And I'm doing that because when we have multiple outcomes, each was going to have an intercept. And to keep track of which intercept that happens to be, it gets really messy in notation. So I just put a superscript there. I don't like superscripts in notation, generally speaking, but it's what I have right now. So we have an intercept. That thing is going to represent what? The mean performance score across all the people. We have error. Error follows a normal distribution with a zero mean and a variance. That variance will be our variance of performance overall in the sample. Both of these, since we're going to use ML, will be biased. At least the variance for error will be biased. The fixed effect is not going to be biased. So, in Lavaan, the syntax that we need to see is very interesting. In R, the way it works is we create a variable, and in that variable you'll see equals, and there's a quote sign, and everything is in green in the quotes. We create a line of text that provides the syntax that goes into the analysis in Lavaan. And if you've used M+ before, this line of text almost perfectly mirrors what M+ does. By the way, M+ is a type of program where you have one analysis per file, right? So if you have like 20 models that you're running, which in multivariate statistics you typically will, you'll have to fit all these different things. You have like file hell in your folder of what you're doing. But in R, we get rid of that. We have this quote. So this quote, everything in green is a quote, but what we end up doing is we put the variable names that we want in the analysis inside of this quote. And the different parts of the quote refer to different parts of the model. And what I want you to look at here is mapping each of these onto a multivariate normal distribution. And that's where we showed up with before. With one variable, there's only one variance though. And the way that we tell Lavaan we want it to estimate that variance is to say the variable double tilde with the variable. This means perf, tilde tilde perf, estimate the variance of performance. That is sigma squared E. That's what that's doing. The part of the quote that has a pound symbol in front of it or a hashtag in front of it, that is not some awesome Twitter handle for variances, right? This Lavaan is so awesome. No, it's just a comment. Although that would be kind of funny. Like, go to Twitter and like look up hashtag variance. I'm sure someone has it. Some of you are looking that up right now. Hashtag means is not the means on Twitter. That basically says I want to estimate per tilde 1. That really means that tilde is like saying the equal sign in a model statement. The 1 there really says that's my intercept. You may have seen this in model syntax and other places in R. I've given you some. Once you create this whole quote, though, this whole string, model01.syntax is just the string itself. It's not the analysis. You take that variable and you put it into this function, this SCM function. Leave the options as you see here. We don't need to get into those just yet. That runs the analysis. And then it puts the result into whatever you put on the left-hand side of the equals. In this case, I'm calling it model01.fit itself. So Lavaan, so if R is a syntax, we think of R as having like syntax for language. Lavaan is an additional layer of syntax within R to make it work, which is a pain, but believe me, it's worth it for this. So now we get two estimates. We get an estimate of this, what we call the intercept, 13.966. That is the mean. And we get an estimate of the variance itself, 8.751. That is the variance for performance. Questions? All right. So here's the thing about a univariate model. Model fit was perfect. This is a plot of what we saw, a histogram of the data and what the model thought the data should be. And we see a pretty good model fit. That's how it always works in univariate statistics. You never really even talk about them. Sort of, sometimes we think about, we got to look at our residuals. So that's like flossing your teeth, right? You really have to every day? Every analysis, do you have to? I floss every day. It's like one of those things where someone openly admits, yeah, I don't floss. Oh, that person, ugh, right? Yeah, you don't floss?
Oh, actually.
Oh, never mind. Question.
Yeah, whatever.
Yeah, whatever. Don't ask them.
On the slides online, there are like both lines going on the previous slide.
Yeah, I don't know where those came from.
Okay.
That's probably like a PDF issue. Sorry. They mean nothing. I did see those actually, but I don't know what they are. Sorry. All right. So that was regression. We didn't put a predictor in, but that was what you knew and loved about regression up to this point. Let's talk about multivariate regression, though. Let's go and provide a model where we get, we're going to predict both mathematics performance and perceived usefulness simultaneously. All right? We're going to assume these to be continuous variables. And right now we're going to look at this empty model because it will give us a baseline, tell us how much variance there is for each variable, to tell us the covariance between them, which when we add predictors, we'll go on to talk about proportion of variance accounted for. Now, this is sort of the baseline for that. We'll also be able to talk about how these look based on the characteristics of this multivariate normal distribution, tying last week's blah 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 matrix test with this week's blah 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 Lavaan. All right. Trying to think of how to like summarize. Normally I hate meetings. If I was sitting in this class, it'd be so hard to pay attention. It's hard for me to pay attention in lecture even. So some of you have been in meetings with me, right? And you know what I'm like in meetings, right? It's like blah blah blah. I'll even type that sometimes to you over like Google, right? Which is blah blah blah. Something blah blah blah. That's my summary statement. That's how I write meeting notes. That's exactly right. Yeah. So anyway, we'd like to talk about the big picture also about multivariate data. We go from 1 to 2 variables. It's not a big deal. There's only 3 parameters in the covariance matrix instead of 1, but it does give us an opportunity to see the different ways that assumptions about it work. So I'd like to show you that as well. So here's our analysis. Here's our model, the notation for it. We're going to come up with 2 regressions. It's a multivariate model. Multiple regressions, multiple regressions. I thought that was funny. Multiple regressions. Anyway, 2 lines. I'm not that funny. I know. I get it. I'm trying to go for like quant funny. You know, it's like a different standard. You know, like Yeah, absolutely.
It's not
Like if you're working in a field, I don't know, like, and there. Sorry, maybe I shouldn't say this. Never mind. Anyways, I'll say it anyway. You know, like there's, like if you're at work, you're at a job, and you know, not a lot of attractive people around, but there's the one person who, by standard in the job, you're like, oh, that person's not terribly unattractive. That's what we call work hot, right? So, you know what I'm talking about? No? Maybe? No? Doesn't work that way? Never mind. It's like quant funny, right? Most of the quant people, I don't know that we have that great of sense of humor. I'm trying to at least be relative to the average for quant, not bad. But like the average person, still well below that, right? Is that, have I gotten myself into trouble? No. Anyway. Okay. This was, I don't do this, by the way. There's no, this was back like, this conversation occurred back when I was like 19, working at Carl's Jr., you know, like in California, working fast food.
So the conversation did happen.
Oh yeah, back then. Like now it may not be the same, but that's a terrible analogy. I just dug myself a terrible hole. I am. Let's talk about two variables at once, though. All right. This is more than the average model. There's two. We're going to predict performance and usefulness. Each of them, if we just looked at the line that they're on, it just looks like a simple linear regression model by itself. And that really is sort of it. But when we go and put them both together, we not only have the two intercepts to worry about, we get this covariance matrix to have to worry about. Because it's the pair of errors that cause everything to be messed up. So in a univariate regression, we always used to say that this error term, disgusted at my own performance here. This thing was normally distributed, right? That by itself. Well, when you have more than one of them, guess what? We're going to take the generalization of a univariate normal to describe them. And sure enough, at the end of last week's lecture, we talked about the multivariate normal, which was a generalization of the univariate normal. So now we have these two error terms. They're bivariate normal, multivariate normal. The mean vector for these things is the zero vector. We talked about it last week. The covariance matrix, which I'm going to label as R right now. The R matrix itself, R for residual variance. Once we predict these will become the residual variances. That now has down the diagonal the variances for each, and the off diagonal the covariance between the two. So this matrix, because it is a covariance matrix, it will be the size of it is it's a square matrix. Remember that from last week? Number of rows by number of columns. Are you throwing food? Anyone want to help Megan open it? No, never mind. Now I'm embarrassing her even more. All right, I'll stop. I'm embarrassed. I'm like trying to share it. You can just share in my embarrassment here.
You said you were going up the line.
This covariance matrix, the square matrix, the number of rows and number of columns is equal to the number of variables we have. So in a multivariate model, even just like this one up here, we have to look at how many outcome variables we have, and that will give us a picture of how many parameters we need to make this thing work. So if we're counting parameters, there are 5 total here on this slide. 1 intercept for performance, 1 intercept for usefulness, 1 residual variance, or in this case error variance for performance, 1 residual variance for usefulness, and 1 covariance between the two. So we go from 2 parameters in a univariate model to 5. And actually, had we run this as 2 separate univariate models, we would have 4 parameters. We wouldn't have this covariance. Okay, so here's blah, blah, blah matrices. We could actually show how this works with matrices. But we'll just go back into Lavaan here. The Lavaan syntax for it looks very similar to what you saw on the previous page. We have to put a section where we call means in place. That's the variable tilde 1. Now, let me back up a second here. I'm giving you the verbose style of Lavaan syntax. There is a way, in fact, if you just use this middle line here, by default it estimates everything. But I want to show you each part of the syntax that goes with each part of this analysis, because each of those will be what we use to go and make parameter estimates and effects, or linear combinations. The GLHT in Lavaan, we have to have access to all of this to make it work. So this means section is like where the model for the mean shows up. That's each of our outcome tilde 1, just to get the intercept. When we put in predictors, they're actually going to show up here. The variances, just like we saw before, the variable double tilde with the variable on the other side estimates the variance for each. And the covariance, believe it or not, is the same. It's just the variables on either side are different, right? So perf tilde tilde use is the covariance between the two. You could have picked use tilde tilde perf and gotten the same result, but just one will do. So here, each of these parameters in this multivariate normal I'm trying to label with this slide itself. And in this analysis, you'll see that we are estimating all parameters in this covariance matrix. So what we're saying, it follows, we're saying it is a saturated covariance matrix. Everything's estimated. In fact, with a multivariate normal, you cannot get a model that fits better than this. This has to be the best model fit because there are no more parameters you can have. There's 5 total parameters possible, and we're estimating 5. We can't estimate more parameters than we have spots for them. So this is a saturated covariance matrix. The word saturated shows up a lot in the path analysis world. If you're in the mixed model world, we call this an unstructured covariance matrix, meaning we're just estimating everything. And if you want to go a step further, this is what MANOVA does, or multivariate regression itself. I'm embarrassed. My ears, I feel like they're turning on fire. I feel like I have glowing ears up here. I'm going to move past my bill. Questions on this while I try to move on? Okay. Yes, Megan.
If you fix the covariance to 0, is that also going to individual?
Yes, actually it is. If you put a 0 here, because these are multivariate normal, the multivariate normal, one of the properties of it that I skipped over quickly at the end last week, I do multivariate normal every night. That implies that the variables are independent if you put a 0 here. Right? If they're independent, then if you were to do them separately, you could add their log likelihoods together and get what you would get from this model. That's 2 questions. Other questions? So here's our estimated values themselves. You'll see here we get our covariance. Let's start with intercepts. The performance intercept, 13.959. The usefulness intercept, 52.440. Well, performance was a scaled score or a number correct out of 20 items on a math test. Usefulness was a kind of a psychometric variable that went between 0 and 100 or something like that. So the mean usefulness. Here are the variances of both. You'll see the variance for usefulness is a lot bigger than the variance for performance. Okay. Does that surprise you? No, probably not. The metrics are different, right? One variable goes from 0 to 20. One variable goes from 0 to 100. So the range is bigger, the variance has to be bigger. Right? Not necessarily if the data didn't. If the range was this, but your data was like this, it may be smaller, but it can be bigger. Most often is. I'm noting that right now because one of the bigger, most strict assumptions that we see, particularly in repeated measures ANOVA, is that the variance of all your outcomes is equal. So if we were setting this up as a repeated measures ANOVA design, we'd make the assumption that these 2 variances should be equal. And Lavaan would do it for us. It'd tell us how bad we were for doing it, actually. We're going to do this in a few slides. But the estimated variance wouldn't be 8 and it wouldn't be 249. It'd be some pooled estimate in between the two. Probably the average of the two. Okay. So that's one way I want to say this. having the flexibility to model that and understanding the assumptions, what they mean, is an important step there. That's one big thing. The other thing is we can see the covariance here, 6.847. My question for you, there's the covariance. What's the correlation between these two, if that's the covariance? Right, we get the covariance. Remember how to translate a covariance to a correlation? So the covariance divided by the standard deviation. This is of let's say xy. Standard deviation of y. So if you wanted to make this a correlation, how would you do it? 6.8747 divided by the square root of 8.472 times 249.245. Right. The nice thing about path analysis software is they've already assumed you might need that, so there's actually a way to go and get Lavaan to give us that correlation by asking very nicely, or using a different function. It's called the standardized estimate. We'll worry about that next week. So this is the multivariate normal distribution that is implied by our estimates. This is a picture of it. It's like a multidimensional bell curve, the taco bell curve, I like to call it. No? Not good? Prefer Liberty bell? No? Do you have a better bell? No?
Saved by the bell?
Saved by the bell curve? I like that. That's my type of humor. That's quant funny. Sorry. Anyway, I think of Bell's. Isn't Bell's a beer from Michigan? I know in Ann Arbor everybody drinks it. Bell's beer. Anyway, this is the density. The mean vector is right there in the middle of the most likely part, and every part of this likelihood shows up. Now, in the homework that you're doing, homework 2, you get a likelihood function. At the end of it, you're supposed to figure out the likelihood of each of the observations. That's like going through all of our data and taking each person's value in performance and usefulness and getting their height for it. Right. And in fact, one thing I didn't show you in the output, but I could have, and I will in a few slides, one of the things that the Lavaan gives us at the end of the analysis is a sample log likelihood. Right. The sample log likelihood comes from plugging in the data. This is the MLE. We want to figure out for each data point what its likelihood contribution or value would be. So if we have a person who's right here, we take the log of that value, we add that to the next person, we add that to the next. So the sample log likelihood is really each person's individual contribution to that big number that happens to be the log likelihood itself. So what you're doing in homework is essentially what Lavaan does at the end. Right? When you have to take the 5 values, get the likelihoods, and then ask you for the sample, right? Some of those logs is what we're doing at the end of this itself. So trying to kind of tie in what the computer's doing with what the theory happens to be as well. But again, plug in value, get height is really what I want you to think about here. Now here is a scatter plot of that same taco bell curve. What was it? Saved by the bell curve over here with the data superimposed. So like we flew over, remember the contours? That's equal height on the mountain. Right? So these are the curve. Here's our data. And you'll see for these two variables, this thing looks pretty good, right? I mean, we got a lot of the data here in the middle, kind of less along the sides. I don't know, there's no standard to compare it to what bad will be, but I'm going to show you some bad versions of this pretty soon, all right? But this is good for several reasons. Number one, I generated these data with the multivariate normal distribution. So these truly are multivariate normal data. Number two, our model is saturated, right? We have all the parameters possible, so we're going to get the best fit to the data. May not be the most parsimonious fit, but it'll be the best. Questions? All right. This is that cursive multidimensionality slide. Here, we only have a couple parameters themselves, but this this is a plot where the green line represents the total number of parameters in a multivariate model based on the number of outcome variables you have. Right? The black line is the number of means that you have, essentially. These are your mean vector size. And the red line is the variances and covariances. So you see this quadratically increasing function. I don't know if it's quadratic or not, but maybe it's this nonlinear accelerating function. Every variable you add not only adds a variance and a mean, but also adds all the covariances with it as well. And that's the problem for what we have to deal with. You'll note that I didn't change my label. I stole this slide from SEM a few years ago. But that's because in the structural equation model, when you put a measurement model in, like the factor analytic part, each of those variables is an outcome too. So it's really easy in structural equation modeling to have 90 outcomes. Multivariate model of 90 outcomes. That sounds crazy, right? How many covariance parameters is that? Don't even bother. All right. So that's that curse of dimensionality. Okay, so let's talk a little bit about this robust maximum likelihood before break. Robust ML still assumes the data follow this multivariate normal distribution. Lavaan, by the way, by default, does robust ML. Robust ML is great. It's great because if your data are pretty close to multivariate normal, maybe there's some peak over too much kurtosis, too much peak, or too flat, it helps you. It'll correct or it'll change the standard errors. It'll change the distribution slightly to make it more appropriate for the peakness or the flatness that's there. So here is a series of kurtosis, distributions with kurtosis. This black line in the middle here is the normal distribution with no kurtosis. And you can see different values of how peaked or flat it might be. So at the end of Lavaan, the estimator equals MLR is how you make this work. I just leave it there always. Never changes. Because if your data don't need it, it works the same as multivariate normal. But if your data do need it, it will adjust it automatically, right? So you put it there and you do your interpretation as if nothing changed. But it adjusts all the p-values, all the standard errors, everything that you need to look at is adjusted automatically for you. So it's sort of like protection against overly peaked or overly flat data for what we have. So I think it's good. That's another example of subsumed, right? This robust ML subsumes regular ML by adjusting based on kurtosis. Now, it adjusts, all these are acronyms and blah, blah, blah. This is more just saying, if you come up with, and when we get into model fit, it'll adjust overall model fit, which we'll see pretty soon. This is based on the likelihood. But more importantly, adjust the standard errors for each of your betas. Why those are important is because the same way that we got hypothesis tests in our first homework, where we had to do GLHT because of the standard errors, they're the same here, but the standard errors, if they need adjusting if your distribution isn't quite multivariate normal. It's too peaked or too flat. So it does it for you automatically. Derivatives, more sandwich. One of the things I love about statistics, this is maybe a little bit better acronym term, something called a sandwich estimator involved in this. Ever heard of a sandwich estimator? What does that make you think of when you hear that? In English, not in statistics. I want the pizza estimator, right? This is a term that describes the function that does this, and there's two identical parts on the outside of it. They talk about being the bread, and in the middle is something else. It's called the sandwich estimator. Wow, it's better than decomposing variance, right? Okay. If, let me just skip ahead here. I'm going to come back to this set of slides in a little bit, but let me stop here and talk about the take-home point. I'd like to get into the model comparisons and then come back to these slides. Use MLR. That's the take-home point. In fact, if you're using M+, Lavaan's, Lavaan's idol, the thing that Lavaan was written to rip off. M+ by default uses MLR, but a lot of times you can override it. Lavaan, it believes in MLR so much that even if you override it, it still adjusts using the sandwich formula. So everything gets adjusted anyway. So your results may not exactly mirror M+, but not a big deal. So use MLR. It's really good. It helps. It's an advance. So that's what we'll do. Questions for me before we get into model comparisons and so forth? All right, let's take a break. Then we'll come back and do model comparisons.